My name is Ivan, and I'm a machine learning engineer in Photomath. I focus on the scanning part of the app, and today I will talk to you about all the things we did throughout the past in our scanning pipeline, and what we do now and what we will do in the future. And that history is also it also correlates with my history in the company as well. So to start, when I got to Photomath 6 years ago, we had less than 10 people working for the product, and now we actually employ in total around 300 people in 2 offices. One is in Croatia and the other is in California. And I assume that some of you already know about what we do, but for some of you who don't, so we develop an educational app that helps students. It helps millions of students each day to learn maths, and I prepared a small video for you to show to you how do we do it. Okay, so the core functionality of the app is that scanning pipeline. So the user takes a photo of their problem, we put it through our recognizer and return a structured version of that problem, which we can then put to our solver system, which then creates a step-by-step solutions for that problem, and we return that to the user. Back in 2014, deep learning was in its early phases. We still haven't surpassed the human level accuracy on ImageNet, for example, and Photomath actually worked without machine learning. It had AI capabilities, but it worked without machine learning. And the recognizer part was actually split in two components. So first component was OCR, which took an image as an input and returned bounding boxes around all the symbols that are on the image. And after that, we had a parser which collected the relevant symbols and combined them into a structured format of a problem. Then we could that structured problem put into our step-by-step solver and return the solution to the user. By 2016, the most requested feature for the app was solving like some really hard handwritten problems, and handwritten in general was pretty tough problem for us because we haven't do any machine learning and deep learning like approaches. And we created a small team of 3 engineers, including myself, and we started investigating object detection, deep learning object detection approaches to OCR problem. And we actually we started doing it, and in 6 months we realized that we surpassed the non-ML approach, and we put it in production. And actually what we still think is that we had in 2016 the first ever deep learning based OCR on a mobile device that runs in real time. But there was a problem that we knew, and that was that the other component, so the parser, was a pretty complex thing, and its development was just like git commits of fix after fix after fix. With every fix, we improved the accuracy a bit, but we knew that we cannot solve 100% of the problems that way. Especially, we cannot do things like geometry or tables or graphs or some other things. So we created in 2017 a Moonshot project called like end-to-end math recognition. And the idea was pretty simple. We have those two components, the OCR and parser, and we'll try to combine it into a single component called like end-to-end math recognition, which would get an image as an input and output the structured version of the structured version of the math problem we want to extract from that image. We created that network using convolutional backbone, and we placed a few bidirectional LSTMs on top of it. And actually worked pretty well, but it worked like typically it worked well on the things we had enough data. On things we didn't have enough data, it really didn't. It didn't work. So the problem was data, and the even bigger problem was data infrastructure, which we didn't have at that scale at that moment, so we couldn't iterate and improve our system well enough. By mid-2020, what we actually did was we had that recognition part. It was doing well. We focused on solving, and we improved our solving capabilities. And at the same time, we were focused on infrastructure as well, and we improved our infrastructure to be able to collect more data, to be able to scrape the data, and so on. And we realized around mid-2020 that our deep learning OCR is aging, and we need to replace it. So at that time, there was a lot of hype going around GPT-3 models and transformer-based networks, and I thought, okay, if we can now like solve so many problems with GPT-3, why, or in transformer-based architectures, why? There is a possibility that we can use it for our problem as well. So. Well, for us, it all started with a scribble, and the idea was pretty simple. So we have the transformer architecture for, let's say, some translation task. We have one language as an input, and we output the sentence in another language. And we just replace it, instead of taking a sentence as an input, we input an image, and we output just like structured version of math problem. We started doing experiments with it, and in a few months, actually in March this year, we got on par with our current OCR-based system. And we saw that by adding more data and doing more experiments, tweaking the architecture, and so on, we really saw a steep improvement, and we concluded that, okay, this is no longer a moonshot, and we needed to get it into the production as soon as possible to all our users. So every year, our biggest release is back to school, when, well, kids get back to school. And it's in September, and we wanted to deploy it to the users then. And it was a pretty tight deadline, because we decided to do it in June. We had only 3 months, and it was a team-wide focus. So team-wide focus was needed, and like most of our team, our AI team, worked on that project, and there was 12 engineers working on it, mostly actually students and interns and juniors, and we could do it with less people, but the idea was that okay, we have a tight deadline, and this is a great project to grow engineers, like young engineers on, and that's why there were 12 of us on that, and it was also a company-wide effort, because our old system was working on device, and our new system is transformer-based. It is a larger network. It cannot be in 3 months implemented on device. We can maybe implement it in like later on device. We can invest time in it, but we wanted to deploy it to our users as soon as possible. So we needed to move our scanning pipeline to the cloud. To do that, we created a torch-based deployment. And torch is something I do not recommend, but we used it because it's just like we tried it, it worked, and we had a tight deadline. I can explain later why I don't recommend it. And we built it on top of GPU-capable nodes on Google's Kubernetes engine on Google Cloud. And the whole infrastructure looks something like this. And as you can see, that match recognizer is only one small thing that we needed to move in the cloud. So we had to be careful because, well, during this talk, around 1 million solutions are presented to our users. So if we fail, we'll really the effect will be really bad. So we needed to do it like step by step. And in September this year, we started with 0.01% of users having our new system, and we tried a bit with it. So we had like canary release, and actually 2 days ago we deployed it to 100% of our users. So every Photomath user now is using our new model. You can try it as well. And to talk about the accuracy of that model, so the old system was working 64%, had 64% accuracy, and it is like the main metric for us. And we thought that it is like the state of the art in that area, and we now have 90% of accuracy, which is like dramatic improvement. And talking of business metrics, like everything that we wanted to go up went up. Everything that should go down went down. So scans per users went up by 70%. Users were so failed scans went down. Number of edited problems. So if user is scanning something and they see that OCR failed and they correct it a bit, that action went down by 40%. And also our clicks to our premium content also went up like by 50%. And generally speaking, like users' interaction with the app was improved a lot, retention and like all those metrics. We had some surprising results. We didn't we didn't need, but it was we got them. This is one example I found, but there are many of it, where our annotators are actually having trouble reading it, and they are really great at annotating. We have an internal annotation team, but they're having trouble reading this kind of problems. But our system is working well. There are even worse examples than this one, but this is the first I found. And also another example is that now even if you scan like a part of a problem, our model is doing a pretty good job into inferring what the full problem is. For example, here you can see that the rightmost data is not in the region of interest, and it still predicts it. Also, the square on top of the rightmost bracket is not even in the image, and it infers it, and it really is in the textbook. So now to talk about the future. So in AI team in Photomath, we don't do just math recognition. Math recognizer is only one of the streams we are working on. Other streams include similar problems, so finding similar problems, some optimizations on our internal marketplace, and some optimizations of content, and a Moonshot block where once math recognizer was. And all that streams are on top of good foundations of two teams, so data infrastructure, which does the data work, and MLOps, which does deployment and cares for our GPU nodes. So three main dimensions in which we are aiming to improve our math recognizer is accuracy, latency, and the domain. So, and the domain is currently the most important thing we are working on. So we want to be able to read geometrical problems, graphs, tables, simple word problems, even things like chemistry, why not, or Sudoku. And in stream of similar problems, we are concentrating on improving, finding similar problems and exact copies of the same problem, because similar problem is something that we can show to the user when they scan for a problem, and finding exact copies of a problem can, even though if we cannot solve it, we can know what are the most common problems that we cannot solve, and even if there are word problems that we cannot solve today using AI, we have our own marketplace where math experts can apply, and they can help us solving problems that we cannot do with AI, and we use it for annotating the problems we cannot solve at the moment, as well as to be able to return the solution to the user. We do many optimizations there as well. We want to find, for example, some frauds there. If some expert is trying to cheat, we are also trying to improve their performance, and we are also interested in content they are generating. For example, if they are generating, if many of them are generating pretty similar content, is probably something that we can automate in some way. And the last stream is Moonshot, and one of the problems challenges we have in Moonshot is in Moonshot stream is understanding word problems. So the input is a textual representation of a word problem, and we want extract all the data from it and structure it so we can put it to our solver. I prepared another video, and that is how Photomath can, one vision of Photomath in the future. So.
Photomath, what is this?
This is a quadratic equation.
What is a quadratic equation?
A quadratic equation is an equation with the variable x squared.
How do I solve this problem?
It can be solved by applying the quadratic formula.
Is this correct?
Congratulations! Your solution is correct. Would you like to graph this equation, practice similar SAT problems, or connect to a live tutor?
Graph, please.
The solutions -3 1/2 are where the quadratic function crosses the x-axis.
Okay, so this is a goal that we are aiming at. And one question arises. So in 2017, when we started that Moonshot project, we realized that we don't have enough data infrastructure. And if we did at that moment, maybe some of those things would have already been implemented. But as you see, we have many interesting challenges going on. And if you are ready to tackle them with us, feel free to contact us. And that's about it. Thank you.
If we have some questions, feel free to ask. Actually, I have. Do you think that high school teachers will hate you after this?
Yeah. So we are we have three audiences. We have students, we have teachers, and we have parents. So students actually use it for helping them, and sometimes also for cheating, of course. We aren't scared of that fact, but we are here to support teaching first. And then we help parents like remembering maths and helping their students with their work. And we help teachers, and many teachers actually today use Photomath when they teach something. They just say to the children, okay, so let's open Photomath and go step by step and explain. Because we have, as you have seen, we have some interesting things like animated explanations of some like simple concepts and so on. And this is something that really is useful for teachers as well, because it's better if it's animated than if it's on the blackboard. So we know that it is used for cheating as well, but we are focused on helping part. Yeah.
Thank you.
I have one question. So just to break the ice for everybody else, just ask the question. How many active users do you have these days, and on how much data are you working at the moment?
So how many users? Okay, around, well, in 2019, I was talking that every single day there are many more active users on Photomath than there are people in Croatia. So there were more than 4 million people using each day, and nowadays it's like doubled or tripled. I don't know about it. I have looked for that data about the scans. Like in 20 minutes, in 20 minutes there are around a million solutions presented. And it's around, I think now we have at this moment maybe around 800 requests per second. So we are on the cloud, so we can measure it a bit like easier. So it's at that scale. And the second question was how much data? Okay, so we collect around at this moment I'd say around 50 images per second, and this is just one it's a part of all the data that we have, and we are working on our improving our data infrastructure to actually when now is like every image is sent to cloud for inference, so we can be smarter into collecting the data, and we can pick only the hardest examples. So we can even collect like a smaller amount of data, but the data that we actually need the most. And we have our team of 50 annotators. 15 of them are working on this problem, and they have a capacity of like 100K images per week. So we need, from that 50 RPS, we need to pick like 100K images each week for them to annotate, and we need to do it in a smart way. So we have a lot of, we call them scrapers. They are like filters that recognize some interesting things in that images and try to prioritize which data to collect. And we are focused on like rare examples, things that we have low confidence levels on and something like that. Yeah.
Yeah, I have one more question. What about different domains, other domains like physics, chemistry? I mean, math is probably the easiest one because it's highly structured language. But if you go to chemistry or physics, which are like related but not as formal, what are your take on that?
Okay, so the approach we have in increasing our domain is that we see what we scan the most that we cannot solve at the moment, and we see that, for example, those redox reactions for chemistry. I'm not a chemist, but that like problem types are pretty common. So we are thinking of implementing them, and this is like pretty similar to classic mathematics. Like it is readable, but for some textual problems, we have other systems that are working. For example, we have a system that recognizes the exact problem, even if it's like textual problem, and we can. If we have a solution for it in our database, we'll just match it and show that solution. So we have like a feature matching system involved as well, and this is how we can even go further than maths and physics and everything. We can actually solve theoretically any problem if we have in our database. But well, it's not machine learning. It's just but it is the feature matching part, but the actual content is generated through that marketplace. Yeah.
Hi, thank you for the great presentation. I wanted to ask you about training this transformer model. I assume there is some transfer learning in the background because you have shown that you also do the inference part when not even the whole equation is in the picture. Mm-hmm. Can you explain this process of training a little bit more?
Actually, it's not transfer learning. We just have we represent the image as a sequence of tokens, and we put it in the transformer-based architecture, which is trained from scratch actually, and we can do it because we have a lot of data. Our data sets are now like 1 million images and annotated images. So we can we don't do transfer learning. We use pre-trained models for like extracting features from the images, and then the topmost part is actually trained from scratch. But it's something that we are also we wanted to deploy it as soon as possible, so there are many things that we want to improve on that architecture, but we are doing it step by step now. Yeah.
Yes. Do you use formulas edited by the users for optimizing the annotation process or for acquiring new label data?
Interesting question. So it is actually it is hard to trust the user and also to capture whether they are actually editing it for like because they aren't satisfied with that the solution we return to them, or they are editing it because they want some similar problem to be solved. Because you have like 1A, 1B, 1C, and so on, and they will scan maybe 1A and then just edit it and see the solution for 1B as well. So it is hard to sometimes to get the info from the users. It is the same thing as when you ask the user, is this solution helpful or not? And if you present it like too fast to them, they will just click on something and they will ignore what the message really is. So it is a bit hard to get that input from the users. But we are now working on having an like ability for the user to crop better the image, so they can correct their crops. So we can maybe remove the whole like bounding box around the image and just have one one dot at the center, and so the user can just point with a dot, not with the rectangular like region of interest. Yeah. Okay.